Hello students, welcome back. Today we will be studying one of the important topics from the chapter of current electricity, that is about drift velocity. So let us get on to the topic. Drift velocity. Don't look at the definition at the onset, as I've always told you that first we will understand and then we will define it. So we will consider a conductor in the absence of electric field. The situation, let us peep into the conductor. Just let us try to look inside the conductor and see what all things are happening over there. So inside a conductor, we know that the electrons, they have been separated from their atoms. Now inside the conductor, there are two categories of things being found. One is the free electrons and the other one the positive ions, which have been formed after the removal of electrons from the atoms. So we have big immobile, massive positive ions. They are massive and they are immobile. Positive ions, and at the same time we have electrons, and they are all randomly distributed. Now, in the absence of electric field, this is something very important. What is the situation? Inside the conductor, what happens if we consider any cross section of the conductor? Then the electrons, they move in such a manner that their net flow towards any specific direction is zero. That means electron has got random motion. I want to give this term random motion. The electrons have random motion. The velocity with which they move, that is called thermal velocity, which is at room temperature, and the thermal velocity is approximately 10 to the power 5 meters per second or 10 to the power 6 meters per second. So this is a very high value of velocity which the electrons have random motion at room temperature. This is the situation at room temperature. They have thermal velocities of this range. But the problem is that these velocities, they are all random. Random means what? If it moves if it moves with this velocity in some specific direction, the electron moves with the same velocity in the opposite direction also. So the net resultant displacement is zero. And we can say the net flow of charge, it is all random. If I would like to specify, then we can specify the motion like this. If I will take away this, then the electron's motion is all zigzag random. It is all zigzag random. Random motion of electrons, and hence the net flow of charge through any cross section is zero. They are moving with a very high speed, yet they are not following any specific direction in the absence of electric field. But what happens when you apply some electric field in the presence of electric field? These electrons, they experience a force of attraction against the direction of electric field. Suppose I have connected it to an electric field like this, then automatically the electrons, all the electrons will experience force of attraction towards the positively charged pole of the electric field. So what happens? They experience some force. Force is mass into acceleration. Here you know that force is charge on the electron into the applied electric field. But here the direction of flow of electrons is against the direction of electric field. So we put it minus sign here. What is the negative sign signifying? That the direction of force and electric field, this is the force of attraction, F attraction, and it is against the direction of electric field. So we have placed a negative sign. And if I put MA is equal to minus EE, I get the value of acceleration as EE by M. This is the acceleration which electron has in the presence of electric field. Why? Because now there is some force of attraction on the electrons which is attracting them against the direction of electric field. Whenever there is force, there is acceleration. But the problem is that the electrons, they get accelerated, and when they get acceleration, they gain velocity. Obviously, they gain velocity and they gain kinetic energy also. But very randomly and very quickly, they collide. It is the collision which destroys the electrons' extra gained energy. But what happens? But this is the situation which is happening in the presence of electric field. But electrons collide. With whom do they collide? They collide either with the positive ions, or with other electrons. They collide. Now what happens? You have learned already about collisions, that when a light body collides with a very heavy or massive body, then the light body loses most of its energy. Most of its energy it transfers to the massive heavy body. So the electron, of course, it had some force of attraction because of electric field. This force of attraction provided acceleration, which led to gain in velocity and gain in kinetic energy. But this collision with other positive ions and the other electrons lead to loss of energy. Loss of energy of the electron, and it comes back to pavilion. Means whatever gain it has experienced, it loses in collision. Ultimately it moves with the electron moves with drift velocity. We call it v drift. Ultimately, so electron moves with drift velocity. Why? Because collisions lead to loss of energy of electron, which leads, so it moves with, so electron moves with drift velocity. So what is the value of this drift velocity? Let us see the value. The electron moves with drift velocity. Now average thermal U, initial average thermal velocity is 0. That we have already seen, because the electron is in all random motion initially. Without the electric field, it's in all random motion. So the motion in any specific direction is 0. Net flow of charge in any specific direction is 0, because it is randomly moving, and the net velocity in any direction is 0. So we are having Vd is equal to U plus AT. Here drift velocity is equal to U average. This is 0 plus acceleration is minus E by m, and the time is tau. This is called relaxation time. This is called relaxation time. Fine. And what is this average relaxation time? So hence we got the expression for drift velocity as minus E upon m tau. This is the expression for drift velocity, because you know that the average initial velocity in any direction, U initial average thermal velocity is 0 in any direction. So if this is 0, then acceleration we have already taken, and tau is the relaxation time. What is relaxation time? It is the time interval between two successive collisions. It is the time interval between two successive collisions. It is the time interval between any two successive collisions, or you can say it is the time in which the electron relaxes. Relaxation time means the time in which the electron is in relaxed state without collision. It is the time gap between the first collision and the next collision. The time interval between two successive collisions is relaxation time. SI unit for relaxation time is seconds, and for drift velocity the SI unit is same, meters per second. It is a normal velocity only, but it is a very small velocity compared to the thermal velocity. The value of drift velocity is 10 to the power minus 4 meters per second. Very small. This is a very small velocity with which the electron drifts inside the conductor in spite of having high value of average thermal velocity, because this resultant is zero, net resultant in any direction. And when you apply electric field, there is force, there is acceleration, but collisions lead to loss in energy, and we finally have this expression for drift velocity. And relaxation time is one new term, time interval between two collisions. And this is how we study the concept of drift velocity. In the forthcoming videos, we will see how we can correlate drift velocity with that of electric current. Thank you.